Okay, so for this problem, what we're looking to do is replace the loading by equivalent resultant force and couple moment acting at point O. So if we were to take these distributed loads off of this diagram, what force could we place at O along with which moment so it creates the exact same loading condition on the beam? Right, so that's what we're looking to find. So let's just start out by the resultant force at O is just going to be equal to the sum of all the forces. Now we have a triangle here, and the area underneath this triangle is just going to be the total force. So this area of this triangle, and we have 50 on this side, and we have the base at 9. So for this one, for this triangle, and it's downward, right? It's all pointing downward, so we're going to have a negative. And remember that the area of a triangle is 1/2 base times height. So negative 1/2 times the base times the height, which is 50. All right. Now let's do the other triangle. Oh, do that wrong. Do the other triangle. All right. And this side is 50. And this side is also 9. And that's going to be upwards. So that's going to be positive. So we would have 1/2 9 times 50 again. All right, so adding these two together, we see that the forces cancel out, and the resultant force at O should be 0. Okay. All right, moving on to finding the resultant moment. So to find the resultant moment at O, we would just take the sum of, find the moments for each of these distributed loads. Okay, so we're going to call counterclockwise positive in our sign convention. Okay. All right, so we have the sum of the force here. Each one of these is 225 pounds. This one's also 225 pounds. This one's negative if you want to consider that because it's downward. So the distributed load on top of 225 pounds will create a clockwise rotation. So that will be a negative value. So we want to make sure that's a negative value. So we have negative 225. And then we need to multiply that for a moment. We need to multiply that by the distance that this force of 225 is acting away from point O. Now, that's a tricky thing to figure out, but we can remember that in a triangle, if we have a distributed load, the cumulative load acts 2/3 away from this side, and this side is then 1/3 here. Okay, so the 2/3 away here, 2/3 of this base is 9 times 2/3, which is 6. Right? Now let's do the other triangle. And the other triangle is going to, the load is upwards here. So it's going to create a positive moment. So adding 225 here. And the distance that it's acting away is 9 feet plus 1/3 of this base over here. So that's 9 plus 9 times 1/3, which is 12. And we figure out that the resultant moment about O is 1350 pound-feet, which we can also write as 1.35 kip feet. Remember that 1 kip is 1,000 pounds. And so our resultant load here is 0 at point O, and then we would be adding a moment here of 1.35 kip feet to create this equivalent loading condition. Okay, so that's problem 4138.